we are going to discuss the consequence of quantum physics. Why atomic dimension systems, the classical physics fails. So what are the important experiments where classical theory could not explain the phenomena takes place? First one is blackbody radiation. So blackbody, the mean, it is black because it absorbs all the radiation. See, if something is appearing black in a visible region, so what does it mean? All the light incident on it is getting absorbed. So there is no light available, so it looks dark. So black or darkness is not a color, it is the absence of color. Okay. So when something is emitting all the radiation, that is also considered as black body. So when something is emitting all radiations in the visible region, let us assume in the visible region, it appears white. So don't think that black body means always looks black. So when it emits all the radiations, it may be appear. For example, sun is a example of black body. Why it is a black body? Because it emits all radiation in the visible IR and ultraviolet range. Okay. So sun is an example of black body. So no black body, no system in the universe is exactly black, exactly a black body. So it absorbs all the radiation, it emits all the radiation. Okay. So there is an extent. For example, if for me my hair is appearing black, that is because visible region it is getting absorbed. It may emit IR, it may emit UV, we don't know. Okay. So a perfect black body means from radio frequency range to gamma ray region, all the radiation is getting absorbed. Then only it is called a perfect black body. Whatever black body we physically see are black body in the visible region. It may emit IR, it may emit UV, we don't know. Okay. So when a metal is heated, it gives off visible light. Whole color varies with temperature of the metal. So metal is heated, for example, iron is heated, first it becomes red, then later become yellowish, and finally it becomes white. The color changed from red to yellow to white as it becomes hotter and hotter. An object need not be so hot that it is luminous for it to radiate electromagnetic energy. All objects radiate energy continuously at all temperatures. This is very important, with their frequency depending on their temperature. All bodies in the world is emitting radiation. For example, human body emits IR, infrared radiation. Okay. At room temperature, most of the radiation is in the infrared part of the electromagnetic spectrum and hence invisible to our eyes. Okay. For example, snakes will sense the infrared rays emitted by the objects. So it can see the IR rays. In one sense, you can say snakes can see IR, infrared rays. Okay. So it can easily identify the prey. On the other hand, we observe only in the visible region, but one can feel the heat radiation emitted by an object. So black body radiation and Planck's hypothesis. All the hypotheses previous to Planck which tries to explain the black body is a failure. Okay. Then Planck understood that there is a basic understanding is required. You have to change the basic in which we are believing. You have to change some fundamental concepts so that you can explain the black body radiation. So notice that black body radiation is a very old phenomenon. It is excellently well established, but only there is no theory for it. The classical theory is unable to explain. So Planck made a quantum theory. The ability of an body to radiate is closely related to its ability to absorb radiation. An object at constant temperature is in thermal equilibrium with its surroundings. This generally students have the doubt. If you say black body is always absorbing, then when it will emit, when it will absorb? It is very simple. When the body's object, when the temperature of the body is lower than the temperature of the surrounding, then the body will try to absorb the energy from the surrounding. So it acts as an absorber. Now, if the object temperature is greater than the surrounding temperature, then the object will emit radiation. Clear? For example, human body will emit radiation, heat radiation. This is because our body temperature is generally 36 degrees Celsius, whereas room temperature is around 30 degrees, 25 degrees Celsius. So we are heat radiated emitter. So we are a heat IR emitter. So human bodies emit heat radiation IR region to get because of the temperature difference. They must absorb at the same rate as it emits energy. A black body is a body which can absorb all energies of radiation and therefore should be able to radiate all wavelengths of radiation. An ideal black body absorbs all radiation incident upon it regardless of its frequency. A black body is a perfect absorber and a perfect radiator. So perfect absorber and a perfect emitter. Okay. So what are the let us assume what are the consequences of black body radiation. This is experimentally verified. The total power of the emitted radiation increases with temperature according to Stephen's law. That is, total power emitted is proportional to T to the power 4. The total power emitted is T to the power 4. Means if I double the temperature, my power increases by 16 times. Okay. The peak of the wavelength distribution shift, that is, the power is a strong function of temperature. The peak of the wavelength distribution shifts to shorter wavelengths as the temperature is increased. Okay. These are the black body radiation intensity as a function of wavelength. So it is what do you call? It is nothing but a spectrum. So intensity is a function of wavelength or frequency. Now at 2000 Kelvin, the intensity of the outcoming radiation varies like this. So around 1.5 micron, you have the maximum energy, maximum intensity. When you heat to 3000 Kelvin, the wavelength at which maximum occurs shift to left. For example, for 3000 Kelvin, this is the around 1 micron, you have the maximum energy emitted. And if you go to 4000 Kelvin, now still it shift to 0.5 micron. So what is the understanding from this graph? The wavelength at which the intensity emitted is maximum shift with temperature. How? Towards the lower wavelength region. Spectral distribution of black body radiation. The 4000 Kelvin curve has a peak near the visible range. This curve represents an object that would glow with yellowish white appearance. So this is the 4000 Kelvin. This is the visible region. So this is the visible region. So this is visible region of the spectrum. So the maximum somewhere lies close to the yellowish region. At a particular temperature, the distributed energy is not uniform. You can see the distribution energy is not uniform. With each and every wavelength, you are not having the same intensity. Some wavelength have maximum intensity, some wavelength have lower intensity, lower. So you have all possible wavelengths, but the intensity emitted by each wavelength is different. That is why you are having non-uniform distribution among the various wavelengths of the radiation emitted by the black body. For each temperature, there is a maximum wavelength lambda m at which energy radiated is maximum. For example, this one 1.5 micron. So this is the wavelength at which the energy is maximum. If you go to 2 micron, it is lower. Here it comes around 1 micron. Here it comes around 0.5 micron. So all the, as I already pointed out, all the theories explained by based on classical theories failed to explain the black body radiation. So Planck took a new idea to explain the black body radiation. Planck assumed the cavity radiation came from atomic oscillator in the cavity walls. This is a model for black body. For example, a radiation is a small opening. If the radiation enters this opening, it will go and keep on reflecting and it will never come out. So this is an example of good absorption material. So this is a model. Energy of an oscillator, he assumed all matter consists of atoms. He assumed all atoms are an oscillator. So they are oscillating their mean position. And the energy associated with each oscillator is hf, where h is the frequency. Here Planck's constant f is the frequency. So he directly connected frequency and energy. This is the first step to a new theory. Before that, what is meant by frequency? Frequency is number of waves per second, number of oscillations per second. This is the definition we have used for frequencies. On the other hand, the first definition came connecting frequency directly with the energy is this Planck's frequency. That is why this constant is in honor of him. This constant is called Planck's constant. The oscillator emit or absorb energy when making a transition from one quantum state to other quantum state. For example, En equal to nhf. That means if n equal to 1, you have hf. When n equal to 2, you have 2hf. Okay. So, in between values are not allowed. So, when an oscillator emit or absorb energy, for example, if the I will put a diagram. This is hf, this is 2hf, this is 3hf, this is 4hf. Okay. So, if an oscillator present here, when it will absorb, if incident radiation come, it getting absorbed and go to this state. Okay. On the other hand, if 4hf energy, an atom having the vibrating with a frequency of f, having energy 4hf, it will come back to ground state by emitting 4hf radiation. So, now when high energy to low energy, it becomes an emitter, and low energy to high energy shift, it is become an absorber. So, these are the allowed values. You can see the energies are equally distant. An air thermometer measures a patient temperature by detecting intensity of the IR emission leaving the air drum. So, the air thermometer senses the IR radiation emitted by the air, and from that it calculates the temperature of the object, human body.